Okay, let's solve this problem together. What we need to do is we need to, of course, store the matrix and the bias as follows. And we also need to store the input x because we need that value for calculating gradient of w in respect. We need to store x because when we need to calculate the gradient in respect of w, we need this value. And another thing you need to note here is we need to keep track of the original x shape when we try to deal with batch samples. I'll tell you why we need this in the next implementation. In your solution, if you haven't included this part, that's okay. Because I didn't mention that you need to think about the tensor case. But this one is to deal with tensor cases. However, if you don't include this part, that means you are just accepting matrices, not tensors. And we are going to store dw and db as well. And in this forward method, what we are going to do is we first need to store the original shape of x like this. And then we'll reshape x's like this. This is to make tensor into matrix. And then we're going to store x like this. And the output is going to be np dot self x and self w plus self b. That is our output. And we're going to return this value. And the backward step, what we need to do is first we need to calculate dx, which is np dot the upstream gradient and the transpose of w. And we're going to store dw as np dot self x transpose times di. So we know this. And self db is going to be np sum d out in the x is 0. And because this backward returns this value, and we need to restore the original shape. This is to deal with tensors. And we're going to return dx. This is just one choice of implementation. If you want to pass dw and db, that's also okay. However, in our implementation, we're just passing dx. Okay, now let's have a look at what softmax regression would look like with backpropagation. Here we're getting input in 3 dimensions, x1, x2, and x3. And this one is get multiplied with our W matrix. And we get our logits here. And here we apply the softmax function. And the resulting probability distribution is compared with the ground truth probability. And then we can calculate the loss. Then how can you calculate the gradient of loss in respect of W12 and W23? This one affects both A1 and A2, like this. We need to calculate this loss. And And the loss in respect of A1 is y1 divided by A1. And this one, the gradient of A1 in respect of Z1 is A1 times 1 minus A1, because this one is a softmax. And dZ1, dW12 is X2, because it gets multiplied with X2. And we just need to follow this mechanism to calculate the gradient of W12. And to understand why this one is y1 divided by a1, you need to think about this. This one is, the loss is calculated as this one because we are using the cross entropy loss or softmax loss. And here, other values are not related to A1, so we don't care about them. But only this value is what we care about. And when you derive this one, it becomes y1 divided by A1. So that's why the first part is y1 divided by A1. And the second part is somewhat tricky. However, we already know how to take derivative of this. To calculate A1, we need to normalize the values, and only Z1 goes to the numerator. And when we expand this part, and refactorize the equation, then we know that this one is A1, and this one is 1 minus A1. Like this. So you can take your pen and paper and derive this on your own. And this one, similarly, you can follow these steps, and this will result in minus A2 times A1. And this is simply X2 because we are calculating this one. This one becomes 1. Therefore, the softmax regression, to calculate the loss, it becomes this equation. So you just need to combine this part. And another thing is, you can vectorize this formula. Therefore, the loss, the gradient of loss in respect of W becomes this. The output minus the A matrix times A transpose, get transposed again, and put minus sign here. So this is kind of recap that when we are dealing with vectors or matrices, we don't explicitly calculate Jacobians, but we just follow this vectorized matrix calculus. So even though it looks quite intimidating when you vectorize or make matrices, then the operations become quite simple. Okay, that was the last example, and let's summarize this session. In this session, we talked about the motivation of computation graphs. What was the motivation? We cannot calculate all the gradients on our paper. And if we switch or change some of the modules, then we need to do the derivations from scratch again. And we want to avoid that situation. And what we do is we modularize every computational blocks and pass the upstream gradients to the downstream gradients. In that way, even though we switch or change some modules, we can still keep track of all the gradients quite easily. So that was the motivation of computation graphs. And we also discussed the calculation of gradients. Here, you need to think about 3 concepts: gradients, Hessian, and Jacobian. gradient for functions with vectors or scalar output. Hessian was also, the input was vector and the output was scalar, but we are taking gradient 2 times, twice. For Jacobian, the input and output were both vectors or matrices. And this was very complicated, and we don't actually form these Jacobians in practice. And we had a look at activation functions in different respects, and we applied the modularization when we discussed computation graphs to activation functions. So what we did was we divide the forward path and backward path. And in the process of forward calculation, we stored some important values to do backward path. In that way, our backward path became efficient. And we introduced some examples, concrete examples. Okay, that's the end of this session.